Hello students, in this video we'll discuss Heaviside's method for computing coefficients in partial fraction decompositions where there are distinct roots. So let's suppose that p of x is a polynomial with n distinct real roots. Then we have Heaviside's result, Heaviside's theorem. And that says that 1 over p of x for this configuration for distinct real roots is equal to the sum, j goes from 1 up to n, of 1 over p prime of xj, x minus xj. Okay, so in other words, the coefficients in partial fractions are exactly the reciprocals of the derivative of the function at the root in question, right? Okay, so in other words, you can also write this as the following form as the sum, j goes from 1 up to n of 1 over p prime of xj times 1 over x minus xj. Sometimes it's written like this, right? So those are the numbers, those are the coefficients that you get in your partial fraction decomposition. So how do we prove this? So proof, so we're going to use partial fractions, of course. Proof by partial fractions (1 over p of x is equal to the sum, j goes from 1 to n, of some numbers aj, which I don't know, aj, over x minus xj, right? So our goal is to find these numbers aj, okay? So how am I going to do that? Well, we're going to construct some auxiliary functions. So define gj of x by the relationship that gj times x minus xj is equal to p of x. So in other words, I construct n different polynomials. So I have g1, g2, g3, all the way up to gn, and they're defined by this relationship over here. So now, what are properties of this function gj? Well, what can I say? I can say, and we impose the condition now also that gj of xj is not equal to 0, okay? If g of x, if these polynomials gj of xj was equal to 0, then that would say that p did not have a single root at a root of multiplicity 1 at xj, right? And then what do we know about gj of any other root, xk? Well, if I plug in any other root over here, xk, I'm going to get a 0 over here, so those other roots have to be 0. So the gj's do not vanish at xj, but they vanish at xk for any other k not equal to j. That's for k not equal to j, okay? Great. And so now with these auxiliary functions, what I'm going to do is the following. So we're going to take our partial fraction relationship and we're going to multiply by p of x. So we'll conclude that if we, so 1 would be equal to, multiplying this by p of x, the sum, j goes from 1 up to n of a j times p of x over x minus xj, okay? And now the point is that I know for each of these terms of my sum, I'm going to replace pj with gj times x minus xj, right? And so this will become what? So this is going to become the sum, j goes from 1 up to n of a j, and then gj x, and then an x minus xj, all divided by x minus xj, right? So in other words, when x at the non-roots of the function p, so I can cancel these things out, right? So this is equal to the sum, j goes from 1 up to n of a j gj of x. Okay, great. And so now the question becomes, and so this formula over here is valid as long as what? As long as x is not a root of p. This is valid as long as x is not a root of p. Okay? However, what can we say? This expression over here is a polynomial. And a polynomial being identically equal to 1 at an infinite number of points, in other words, there's only n roots of x, so there's an infinite number of other points which this polynomial is equal to 1, that forces the polynomial to be equal to 1 everywhere, right? So by the identity principle of polynomials, this forces 1 to be equal to the sum j goes from 1 up to n of aj, and then what? And then gj of x for all values of x. In particular, I can plug in the values that correspond to any root of this thing over here. So in particular, if we plug in xk, for example, so plugging in xk, plug in x equals xk. And so what do we know about g? So if I plug in all of the values in this sum are going to collapse, right? Because I know that anything other than this, so I know that, for example, g1 of xk is going to be equal to 0, g2 of xk is going to be equal to 0. So the only time it's not equal to 0, we get to point k, right? So if I plug in xk to this, what will we conclude? We will conclude that 1 is equal to aj, ak, and then gk of xk. All right, so we need to compute the value of gk of xk. Well, what can we say over here? So let's figure out what that value is going to be. So how can I compute gk of xk? Let's go back to our original equation. So what I'm going to do over here is I'm going to differentiate this star equation over here. So what will that tell me? That'll tell me that p prime of x is equal to what? Is equal to, well, by the product rule, it's going to be g prime of x times x minus xj plus gj of x times just 1 over here, right? So if I plug in xj into this formula, p prime of xj is going to be what? This first term over here is going to be 0, and this term is going to be just gj of xj. So by plugging in into this formula, xj, I have that p prime of xj is just gj of xj. So this gk of xk is exactly equal to p prime of xk. So this says that 1 is equal to ak p prime of xk. Therefore, ak is exactly 1 over p prime of xk. And so in this expression over here, I can replace the ak with what? The ak is equal to 1 over p prime of xk, and that proves our result. Thank you very much.